the movies, like, okay, now the first one was...
It's okay.
Can you make it a bit more...
It's okay. So welcome everyone, and so I'm very happy to introduce today's speaker, who is Gabriele Benedetti from the University of Heidelberg, and who will help us take our first steps into the world of systolic inequalities. Thank you very much, Gabriele, for agreeing to talk, and please, the floor is yours.
Thank you very much, Federica, for the nice introduction, and to the organizer for inviting me to speak at the seminar. So today we are going to talk about the systolic inequality, which is a type of geometric inequality, a bit like I think you saw 2 times ago the isoperimetric inequality in Marcello's talk. This inequality is classically formulated in the realm of Riemannian geometry. And this first talk will focus on this classical setting. In the second talk, we are going to see that this inequality actually can be phrased in a more general setting, the setting of symplectic geometry. And we will see that this leads to some very nice open problems also today. Okay, so I will start then the talk. And so the Riemannian geometry for us today will be Riemannian geometry on surfaces. So we want to do geometry on curved spaces, and curved spaces for us will be modeled on some Euclidean space of some dimension. And for us, in this first talk, the dimension will be always 2. So we have something which is locally some isomorphic to R2. For simplicity, we take everything with compact and without boundary, and also connected. Okay, and for us, a surface as a first thing is a topological object. So there is still no geometry entering the picture, and topology then allows us to classify surfaces. We have the most simple one, the sphere here on the left, and then by attaching cylinders, or also called handles, we can construct more and more complicated surfaces. And here I also stress that a surface can be, in our mind, realized in very different ways, both as embedded surface in R3 or also using some kind of quotient construction, maybe you know already from topology. And then this gives the first row of orientable surface, but there is also maybe a less intuitive word of non-orientable surface. The first one here is the projective plane, where we take a sphere and identify pairs of antipodal points. And then by attaching Möbius strips, this time we get also here a hierarchy of surfaces, the Klein battle, and so on. So these are topological data, and on this topological data we want to do geometry, and this is done by defining a Riemannian metric on sigma, which we can think about an inner product on every tangent plane. And then once you have this inner product, you can use it to measure things. So the first thing you can measure is lengths of curves, just by integrating the speed of the curve in the interval. Or you can also now measure the angles between tangent vectors. So you know the cosinus of the angle will be given by the scalar product between u and v normalized. And now once you know about lengths and angles, so you know when two things are orthogonal, you can also speak about areas, simply by saying that infinitesimally small rectangle with sides of length 1 and orthogonal as area 1. And then this gives you a notion of area element, and you can integrate it and get the area of region. So here we stress that this G is not at all unique. Okay, so on a given topological data, you have many metrics, and we call R sigma the space of all these metrics, which here we will always consider up to isometry. So basically I want to identify things which are the same in different coordinates, and scaling. Okay, also this is not very interesting if I just take a metric and I scale all the lengths and areas by some constant factor. So this space R sigma is a very big space, and this you can also understand by looking at different embeddings of surfaces in R3. No? So here, for example, I drew some embeddings of the torus in R3, and you see that you can get very different type of geometries. So the question is, how do we put order in this big mess, in this big space? And here we can have maybe two approaches that we will see they are also related to each other. The first approach is to look for special metrics inside R sigma, so matrix G0, which has some nice symmetry properties. No? So for example, in the case of the sphere, you can think about the round sphere in R3. This is a very symmetric case. The other way to study R sigma is to look at how, using G, we can compute size of objects inside the surface. So we see compute length areas, and this gives you different size for curves or regions inside the surface. So then you can see how different metrics measure differently. Okay, so let's go first and look at A. So here we can do a bit case study. So if you look at symmetry, the most intuitive thing to look at are curves are metrics of constant curvature, which are kind of look the same, we can say, in every direction. And then if you have constant curvature, you know this theorem of Gauss-Bonnet, which relates topology and geometry. Basically, it tells you that the topology already gives you the sign of this curvature. So on the sphere or on the projective plane, that the curvature is positive, and your metric will be unique up to isometry and scale. Now, this is just the round sphere in R3. On the torus or the Klein bottle, you have flat metrics, meaning that the curvature is 0. And for the purpose of what we need today, we'll just consider T2. And then a way to obtain this matrix G0 is not by embedding in R3, this cannot be done, but simply by identifying opposite sides of parallelogram. No? So here you see you can identify by translation the left with the right, and then the bottom with the upper part. But this is by no means a unique way to do this. Now, for example, here you can cut along the diagonal and get back a new parallelogram, which gives you the same metric. Now, so already here we find a very interesting problem. How can we classify this matrix? And this is a classical theorem saying that if you want to classify flat metrics on the two torus, you can just do as follows. You take as a horizontal edge here the horizontal edge of length 1, and as the vertical side, you can take any point which is inside this domain gamma. Now, where gamma is basically the part outside the unit circle where x, the first coordinate, is between 0 and 1/2, and y is bigger or equal than 0. Now, then if you have now these two sides, you identify uniquely a parallelogram. And then the theorem says basically that if you take two parallelograms in this way, the metrics are never isometric. And also this is a kind of full classification in this case. And then now if you go in for higher genus, so if you touch more handles or more Möbius strips, then the things becomes more complicated. So I cannot make justice in this talk. No, there is a lot of maths going on there. And but what we now want to stress is that knowing these particular types of metric tells us something also about general metrics. And this is because we have this so-called uniformization theorem. Now that basically says that if I take now another metric on my surface, then I will always find a metric of constant curvature, like the one I described before, and some scaling factor f, which might depend on the point, such that our G is up to this scaling factor G0. So just take G0 and you just scale it in every point in a different way. And this is also the same as saying that G is conformally equivalent to G0, meaning that they basically give you the same angles, but not the same length, equivalent to G0. Okay, and then this is like very short introduction to how constant curvature metrics can help us classifying general metrics. So here we see that we just need to know a function, to know the metric. And now I want to instead give you the second kind of way of putting some structure in this space of metrics on the map. But before, maybe this is a good time if you have questions or remarks. I should go faster, slower.
No, I think it's very good.
Okay, very good. So then let's see then how we approach the second way of studying metrics. And this is for us today through the notion of systoles. So a systole is a particular kind of curve on our space. And it's a curve which has kind of minimal length among non-contractible loops. No? So if you look up here, again, in this case of tori, you see that if you kind of draw a curve going around the torus, then you can always try to minimize its length. And you can do this for every homotopy class. Okay, and then in the end, you will find like a curve which has minimal length among all non-contractible loops. Now, so for example, I don't know, here maybe something here. So this would be the systole. Okay, here maybe it's somewhere here. Okay, and then for us, the systole will always be the shortest non-contractible loop. So for example, if you look here, this curve will not be a systole, because it's a contractible curve if I look now on the right side. Okay, so this is our object we want to study. And then the first thing is that one has to know that such an object exists. And this is a classical theorem of Hadamard for surfaces, saying that if you have a non-simply connected space, so in our case, it simply means we are not looking at S2, then you will always find a non-contractible loop of minimal length among non-contractible loops. And then also what we know from the theorem is that this gamma is a periodic geodesic. Okay, so periodic here just means that you have like gamma, which is a curve on your surface. And then there will be some t bigger than 0, such that gamma t plus capital T is equal to gamma t for all times. Okay, so that the curves goes around infinitely often, so in a periodic fashion. And we will always consider in the following, when we say period, kind of the minimal period where this happens. So the minimal t such that you have this periodicity. And then by geodesic, we mean curves which have 0 acceleration. So here I'm a bit sloppy, so this is 0 acceleration. And this acceleration, you have to think that you have to take it with respect to the metric G. So if you think you're embedded in R3, then this is just the tangential component of the acceleration of the curve in R3. So here, by looking at minimizing this problem, we find a very particular type of curve solving a differential equation, this one here, and we call this curve geodesic. Then I already introduced this notation. So we say that any non-contractible loop of minimal length is a systole. So this is the definition we give here. And then we use the notation sys of G for the length of this systole. So this is just some kind of positive number we associate to a metric. You can think this is a way to measure, to give the size of a metric. And then now, if you look at the pictures above, you see that basically, if your what you can have here, you can have a short systole. Now, for example, in the case here, on this case here, or in this case here. So the systole is relatively short, but the manifolds are actually big. Okay, so this means that if you have a systole which is small, then you can always add some part of the manifold, make it bigger. And here by bigger, you have to measure it in some way. So you can use, for example, the diameter of the manifold or the total area of the manifold. But actually now if you want to do the other way around, so if you now ask if you can have a long systole for a small manifold, this actually it's less intuitive that you can do it here in these pictures. And actually this is kind of the question we want to address. So the question we want to address is that can we have a long systole on a small manifold, where here small, you measure it in some way, the diameter, the total area, and so on. So you can think of this as a kind of qualitative question. Okay, and here basically the question about the diameter, we will not get into this. So this is actually not difficult to show that you cannot have a small diameter if you have a long systole. More interesting is the case of the area. And this is brings us to this more quantitative question. Now, which is here in this green box. So the question now, if I give you a metric G, then I can compare the systole with the area with some like right scaling, because systole is length, area is length square, so to say, so you have to scale it properly. And the question now is that given sigma, if you can find a constant such that this so-called systolic ratio is always bounded by this constant C. Now this should be independent of the metric. Now, so this you can think of this as a way to study the space R sigma. And then in case you can say, okay, yes, I can find this constant, there are many more questions that you can think of. So what is the optimal constant, for example? And are there metrics realizing this optimal constant? So are there metrics maximizing the systolic ratio sigma? And so this is for a surface. This is like this question can be answered in the affirmative. And the first result was established by Löwner at the end of the 40s, saying that actually there is a systolic inequality on the two torus. The optimal constant is 2 over square root of 3. And you also have a unique metric realizing the constant, which is given by the parallelogram, where you have the two sides which are equal, and the angle between the sides is 60 degrees. Okay, so this, you can think of this as two equilateral triangle glued together. Okay, and then, for example, if you go back to this classification here, this is exactly this point here. Okay, you can think of this as exactly this point here. So this is equal to this, and this is 60 degrees. Okay, so now, like, I want to give a kind of sketch of a proof. What are the ideas going into the proof of this result? Before doing that, I have to mention that this classification of flat tori using this this domain capital gamma has also another very important property, is that we can see on the nose a lot of systoles in this representation. Namely, all the horizontal curves are systoles in this, when we use this representation. So this, in general, is not true for every. So these are all systoles. Okay, so these are kind of non-contractible and closed because you identify the two opposite sides of parallelogram, and these are actually systoles. So it's not maybe clear from the picture, but actually you can show this. Okay, so then let me tell you what goes into the proof of this result. Actually, the first ingredient is what we saw in the first part, in this part A. So you want to use as the first thing that your metric G is conformally equivalent to some metric G0. Now this, you know that it's possible by theorem 1, and G0 now will be some of these metrics coming from theorem 2, this metrics classified by the domain capital gamma. And then basically you prove the inequality in 2 steps. So the first step is to show that the systolic ratio is of G is less or equal to the systolic ratio of G0, your metric which is flat. And then the equality happens exactly if this conformal factor is constant. And then the second step is to find among all flat metrics the one with bigger systolic ratio. And then if you see that this is this metric G star is exactly the one maximizing systolic ratio. And if you see this picture here, it's clear why. No, because this is the parallelogram which has the shortest height, no, and therefore the smallest volume, and therefore the the area. Therefore, the area is on the denominator. The systole is always 1 for all these parallelograms. So you see from this picture that having the smallest area gives you the largest systolic ratio. And you see from the picture that among flat tori, the one here making the 60-degree angle is the one with biggest systolic ratio. Okay. Now maybe this was already motivation for 2. Now maybe I can give a short motivation for 1. So maybe let's do kind of proof of 1 let's say in a particular case. So when this G0 is actually the parallelogram which has right angles. So this is more intuitive to understand. So the first horizontal side has length 1, and say the vertical side has length A bigger than 1. Okay, so and now what you do is you compute the area of this of T2 with respect to this metric G. Okay, so now the metric G0 is just the Euclidean metric on this parallelogram. So basically you are just doing the integral from 0 to A, integral from 0 to 1 of f squared s ds and dt. Okay, so this is just the area of T2. And now you can think that using Fubini, now you're integrating this function here in the red brackets. And for this function here, now what you see is that you can basically bring the square outside the integral. So this will be bigger or equal than the integral, let me put it here, bigger or equal than the integral 0 and A, integral between 0 and 1 of f s t ds squared dt. Okay, and now what we have inside the integral is the length of the curve at height t. Okay, so this is now inside the integral. This is the length with respect to g of the curve s goes to st. Okay, but these are these horizontal curves, the length with respect to g, but these are non-contractible loops. So this is always bigger or equal than the systole of g. Okay, and then if you plug this in, then basically now you're done because this is bigger or equal than the systole of G squared times A. And now if you see what this A is, this is A, you can think about A times 1 divided by 1 squared. And this is the the area with respect to G0 of T2 divided by the systole with respect to G0 of T2 squared. Okay, and then basically this, if you read from beginning to end what we've done, we actually prove the systolic, the step 1. Okay, so I wanted to show you a bit in detail this proof because now we can kind of understand what are the ingredients. So it's not important that we remember the things of the proof, but now I want to comment which were the 2 key ingredients of the proof. The first key ingredient was that we had a normal form for G, no? That we used in the first place here, that we can write G as f squared times G0. So we have like a normal form using uniformization. And then as a second thing, we use this inequality between arithmetic mean and quadratic mean on some family of systole for G0 foliating T2. No? So the important was that our systoles for G0 foliated the torus. Okay, so and then we will see in the next talk that this idea kind of comes back also in the case of symplectic, this systolic inequality in symplectic. Okay. Also, I forgot to mention this before, but on the website of the seminar, you find a link to a Dropbox folder, and you find also the slides of this talk at this Dropbox folder. So, for example, if you miss some passages or you want to look back at something, you will find PDF file for this and the next talk in the Dropbox folder. Okay, very good. So this was the very first kind of systolic inequality proved. And is there any question on this result? Or shall we go on and see the others? Okay, so then let me continue. So this was the first kind of systolic inequality. And then now you can ask them what happens for the other surfaces. So the first surface we encounter is the projective space. And this is the systolic inequality here was proven by Pu, who was a student of Loeffner. Here also, the systolic inequality is fully proved. So you know that the optimal constant is pi over 2. And the optimal metric is unique, again, and is given by the metric with constant curvature. And also in this theorem, the technique is the same. You know? So if you look at the remark, you can basically use the same technique for proving Pu's theorem once you know how you prove the Loeffner. And then you can still go on. You can do pretty well for the Klein-Buttel. So for the Klein-Buttel, you still know the optimal constant is this pi over 2 square root of 2. But still here, things are not so nice anymore because the maximizing metric is not smooth anymore. So this means that there is some kind of sequence of metrics converging to this optimal value, but then in the limit, you don't have any smooth metric. And a way to think of this non-smooth metric is that you glue 2 Möbius strips together, and each Möbius strip has constant curvature 1, and then you will, by gluing them, you will have some kind of corner. You cannot smoothen this out. And then after doing this, then basically you go to kind of another planet or other, you need other techniques because if you want to establish a kind of sharp sharp systolic inequality for higher genus surfaces, then this is given by this theorem of Gromov, which basically says that even though we don't know the exact constant, we still have the optimal behavior with respect to the genus. No? So here, if you have genus K, then you expect this constant here, the optimal constant, to go like logarithm of K squared divided by K. No? So you can think about this is that you just kind of sticking many, in the orientable case, you're sticking many tori all together. And so kind of you imagine that the area will grow, but the systole will remain basically constant. So you expect in some sense this constant here to go to 0 with the genus, but still getting the right behavior with K. This is a very deep result. And actually, using the techniques of Loeffner and Pu, you can also establish some sort of systolic inequality, but the constant here will be very bad. So will be very far from being optimal. Now, so from this kind of innocent results, we go to theorem of Gromov, which is very deep, and also it uses techniques which are very far from the techniques we will see today also in the talk of symplectic geometry. So I put it here just to give a complete picture. Okay, so this is kind of a small survey about systolic inequalities on surfaces. And now there is kind of one thing which is missing is what happens on S2. So far we assumed to have non-contractible curves. So S2 is ruled out. Can we define a sort of systolic inequality also for S2? And here the key is that what was kind of a consequence of Hadamar's theorem. Hadamar's theorem told us that if you look at the loop, non-contractible loop of minimal length, this is a periodic geodesic. So in general, you might want to define a sort of weak systole. So this is not like standard definition, but I use it in this talk just to give you an idea. Now you just look at periodic geodesics, which are non-constant, and you took the length of the minimal one. Okay, so you take basically the shortest periodic geodesic, which is non-constant. This you call it the weak systole, if you like. And then the length will be cis tilde in my notation, and you can correspondingly define a systolic ratio by comparing the weak systole with the area. Okay, so if your standard systolic ratio was already bounded, then this sigma theta will also be bounded. But now we have a kind of a chance to ask if on S2, this weak systolic ratio has a bound or not. And so as in Hadamar's theorem, the first thing to do is that we have to be sure that there exists at least one object. So there exists at least one periodic geodesic. And this is given by the Birkhoff's theorem. So now basically we cannot minimize the length of loops anymore because we will just shrink to a constant loop. So the idea of Birkhoff's theorem is to consider one parameter families of loops, which start from a constant loop and end on a constant loop, and then try to minimize in a smooth way the length of the family. And then by doing this, you will end up to some geodesic. Okay, so this...
you mean maximize, maybe?
You will try to make the length shorter.
Oh, you minimize the length of the maximal geodesic, sorry. Yes,
right.
Okay, yes.
Yeah, right, it's a minimax. So, right, very good. Thanks. Right, so this is a kind of very rough idea to show that you expect also in the case of the sphere to have such a periodic geodesic. And now it's a theorem of Krook that actually not only this periodic geodesic exists, but they can also estimate the length of the shortest one using the area. So this means that we have also in this case a systolic inequality. And then the optimal constant known so far is due to Rothman, and is this constant 2 square root of 8, which is the kind of the best bound, but it's conjectured not to be the optimal constant. So the optimal constant is conjectured to be this 2 square root of 3. which is the systolic ratio of the so-called Calabi-Crook sphere. The Calabi-Crook sphere is also, in this case, a singular metric, where you take just two copies of an equilateral triangle and you stick down the corresponding sides together. And then the height of the triangle, going once up on one side and down the other side, will be the systole in this particular case. And right, so this is a kind of the first open conjecture that I present here, and then in the next talk, there will be many, many more actually. Very good. So this is still something, but now if you look at what happens with a round sphere, you find something which is not very nice from some point of view. So the round sphere is not a maximizer of the systolic ratio, because the systole of the round two sphere, sorry, the systole of the round two sphere is 2 pi, so the great circle has length 2 pi. The area is 4 pi, so then we get a systolic ratio pi, which is strictly less than 2 square root of 3. So G0 is not a global maximizer for the systolic ratio. And then I think at the beginning of the year 2000s, there was much research going in this direction. And the people started suspecting that G0 is at least a local maximizer. So meaning that if I start the round metric and I deform it a bit, then I cannot make the systolic ratio bigger. So in the large, I can, no, because I have these Calabi-Crook examples. But in the neighborhood of this round sphere, there was this question to ask if this was possible or not. And actually now we know that the round sphere is a local maximizer, but also the story is more interesting than that, because this local maximizer is not unique. There is a whole class of local maximizer, and these are the so-called Zoll metrics. So a Zoll metric is a metric where all geodesics are periodic and have the same minimal length. No? So you can think of this really as a generalization of a metric on round metric on S2. And then we can define Z sigma, just a subset of Zoll metrics inside the Riemannian matrix of sigma. And now, so these metrics were introduced now more than 100 years ago. So there is a lot of things we know about these metrics, but still also many things still mysterious. So the first thing we know is that having a Zoll metric for a surface tells you something about the topology. So for example, if you know that you have a Zoll metric, then you're either the sphere or P2. And this is really something that you prove from using topology. You prove that if you have a Zoll metric, then your fundamental group is either trivial or has two elements. No? So this gives you exactly these two cases. And then I think at the end of the 50s or beginning of the 60s, there was a full characterization of Zoll metrics on the projective plane. This was done by Green, who showed that there is actually only one of these. This is the round metric. So nothing very exciting is happening here. But the real excitement is on the two sphere, because now in this case we have lots of examples. And you can find examples also with very easy formula among surfaces of revolution. So this is the example I write here. No? So you can write this in using polar coordinates, theta and phi. And the only thing you need is to perturb the standard round metric in polar coordinates using a function h of the cosinus, which is has some property here. So it's odd, and h of -1 is equal to h of 1 is equal to 0. And this is these are where the first examples were discovered by Zoll, although maybe with a different kind of bit of different formula. And hence the name Zoll metrics. So Otto Zoll, student of Hilbert, in his PhD thesis actually constructed the first Zoll metrics on S2. And so this is only like the beginning of the story, because then many more examples were found. And actually, the kind of deformation problem was solved by Victor Guillemin in the 70s, asking if I start with a round metric, how can I deform it and still remain a Zoll metric? Also, and basically the possible deformations are, the tangent space of possible deformations is parameterized by odd functions on the two sphere. Not just meaning that this psi associate to antipodal point opposite numbers. And then if I now consider a deformation which is conformal, I can ask when this deformation is Zoll. And Guillemin showed that I can find one which is Zoll when the deformation has tangent vector exactly this psi. Okay. Also, the converse is true. So if you have a deformation of this type, then it must the f dot 0 must be odd. This was known since the 20s, or I think even before. But Guillemin really proved using the hard implicit function theorem of Nash and Moser that that actually you can construct for every psi a deformation for Zoll metric. So this in particular means that you have an infinite dimensional space, because these odd functions are kind of also here infinite dimensional space. Still, this space of Zoll metrics on S2 is very mysterious. So, for example, you don't know if it's a connected space, or if constructing example beyond these deformations on or the surface of revolution is kind of difficult, even though there is also today some more work in this direction.
So can I ask a question about that?
Yeah.
How do you check from a metric, like if it's Zoll? Because I can imagine you're just trying to write down some differential equation, like from this or something like this, and then you check that it's Zoll, and then you get this condition out of it. Or is that really not how you prove these things?
Right. Yeah. So you can actually, the way you can think about this is that you, if you have something which is Zoll, which you know, for example, you start with G0 and you want to deform it such that it stays Zoll, then basically in the deformation, you are deforming each curve so that it stays a geodesic for every deformation. So it's like you're having kind of one family of functionals, the length functionals. Yes. Yeah.
Okay.
And then, yeah, and this gives you a linear condition. Okay, thanks a lot for the question. It was interesting one. So, and now we come to the like, how can we study this local maximality of Zoll of the matrix G0? Okay, and this actually we will see in the next talk that we'll use a symplectic. We'll use symplectic geometry. So, and here we have this basically these three results. So all three of them actually we will see next talk how they come about. So the first thing is that actually for every Zoll metric, the systolic ratio is equal to pi. So just like was the systolic ratio of the round metric. Now this is a theorem of Weinstein, also I think in the 70s. And also, the systolic ratio does not distinguish different Zoll metrics. The first thing. And then the second result is by Abondando, Brahman, Riniewicz, and Salomao. And is telling us that Zoll metrics are exactly the local maximizer of the systolic ratio. So if you start with a Zoll metric G star, and you consider a small perturbation G, and here you can also put topologies. For example, I think their argument work in the C3 topology and can be also made a bit more precise. I think also they can now achieve also C2, but I'm not completely sure. Then the systolic ratio of G is less or equal than pi, and will be equal to pi exactly when the metric is Zoll. So you can rephrase this really as saying that Zoll matrix is like a subset inside the space of metrics where the systolic ratio has a strict local maximum. And this strict local maximum is equal to pi thanks to Einstein's theorem. And then the question now is, on one side, these Zoll metrics are not global maximizers. On the one side, they are local. So where is the boundary between these two behaviors? Can you how much can you enlarge this this neighborhood? No? So this is, I think, a very interesting question, but it's not much is known actually. So where this this boundary lies. In the actually ABHS also gives some kind of curvature condition. So the result is a bit more precise, saying that if your metric has some pinching of the curvature, then you know that the systolic ratio will be less or equal than pi and equal to pi if it's Zoll. Now, so this tells you that you know something about metrics which are pinched, for example. Another very interesting result is that you know also something very strong for metrics which are coming from surfaces of revolution in R3. And basically, these are also very recent result by ABHS. They can prove that they can prove that also in this case, the Zoll metrics are maximizing. Okay, so if you take just surface of revolution, then among surface of revolution, Zoll metrics are actually global maximizers. So they will be not globally if you remove this hypothesis on surface of revolution, but with this hypothesis, they will be also global maximizers. Okay, and then in the next talk, we will go into see a bit how symplectic geometry can help us in understanding these three theorems. In particular, I think we will focus on this one. Okay, and also like a way to think about what's the role of symplectic geometry in this is that we started with geodesics. So geodesics are solutions of second order differential equation. And this gamma dot dot equal to 0. And now you know from a class in differential equations that you can always pass to a first order differential equation by doubling the number of variables, by taking also the velocity into account. And then this gives you, you can call this Z, gamma dot. And then you will have that this here holds if and only if Z dot is equal to X of Z, where this X here will be a Hamiltonian vector field. So you can basically now look at geodesics as flow lines of a Hamiltonian vector field, and this will be then used is then used in these theorems to for the proof, actually, and this will come then in the next talk. So I will finish here, and thank you for the attention. So we have a lot of time for questions.
Okay, yeah, thank you. Thank you very much. We got so Thomas, you keep recording or well, no. Excellent. So welcome back to part 2 of today's seminar. And we are now venturing into the world of symplectic geometry. I think at least that was promised at the end of part 2.
Yes.
So please, Gabriele, again, the floor is yours.
Okay, thank you very much for the nice introduction. And can you hear me? Yeah. Okay.
Yes, we hear very well.
Okay, very good, very good. So in the first part, we learned something about the systolic inequality in Riemannian geometry. That's where the classical framework is. In this second part, I want to tell you something about the generalization of this inequality in the realm of sympathetic geometry. And this will bring us basically in kind of two fields. So one field, we will see that we can formulate some kind of inequality related to capacities in symplectic manifolds, which look very similar to the ones we saw in the first talk. And on the other side, so the second thing is that we will see that the inequalities of the first talk actually can be reformulated in a symplectic language. Okay, so let's then get started. So I will start by recalling some basic facts about symplectic geometry and Hamiltonian systems that then we will use in the following. So we will start very simple with Hamiltonian systems in a standard phase space. So we are considering here a space of position and momenta, which we can think now in n dimensions. So if you want, you can also take n equal to 2, but what we will say will work in any dimension. And then for every function h on our phase space, we can define an ODE, which is classically called as Hamilton's equation. So I can then consider curves qt, pt, solving the Hamilton's equation. So q dot will be equal to dh dp, and p dot will be equal to minus dh dq. Okay, so this is an ODE, and actually, like every ODE, you can also rewrite it using a vector field. So if I call now z the vector of all coordinates, let's say, then this ODE here, you can write it as z dot of xh of z, where xh is simply the vector field that you get by putting first dh dp and then minus dh dq. And if you want to get now a coordinate-free expression for this vector field, which is also useful for us in the following, then you need to introduce a canonical symplectic form, which I denote by omega 0. And it's just the wedge of dpi and dqi. So this wedge simply means antisymmetric product. No? So you take dpi times dqi minus dqi pi. And then once you have this omega 0, then your xh is simply the symplectic gradient of h up to sign. So you might be familiar with the notion of gradient from Riemannian geometry or simply from standard calculus. And here you do the same. Basically, you take the differential of h, and then you get the vector field xh by duality with this omega 0. No? Instead of having the Riemannian metric as usual, now you have this omega 0 giving you the pairing. And then just as a notation, we denote by phi ht the flow of this vector field. And one of the first things you learn in a course on Hamiltonian systems is that the energy is preserved along this flow, where as energy we usually understand the Hamiltonian. So this is like the physical motivation. And then the reason for this, it's like quite general, comes from the definition of xh and from the fact that omega 0 is antisymmetric. No? So you see here, if I now take the differential of h along the flow, then I know that by chain rule, this is dh times xh. because the flow has tangent in the direction of h. And now by using here this relationship, you get omega 0 of xh, and since omega 0 is antisymmetric, we get a 0. No? So this tells you exactly that the energy is conserved. Like the classical examples are Hamiltonians, which are kinetic energy plus potential. Here I brought one particular example, which is the harmonic oscillator. So this you can think of n harmonic oscillators, which are uncoupled oscillators and have frequencies with frequencies now AI over P. Okay, so you can think in every coordinate QI, PI, you have like kind of harmonic oscillator, and then you have different frequencies. So also here you see that, for example, if the AI are all the same, you have a motion which is fully periodic. If not, you have some kind of quasi-periodic motion. And then this setting that I'm presenting now in R2N, actually you can generalize it for more general spaces. You can actually take any manifold M endowed with a symplectic form omega. No? Where now in general a symplectic form is just non-degenerate to form, which is also closed. The omega is equal to 0. And then the non-degeneracy allows us to basically write symplectic gradients, no? And then have our Hamiltonian systems. And then the closeness condition tells us basically that locally all our symplectic manifolds look like the model we just learned, the model of R2N. And then as like the prime example for us, which is relevant for the first talk, is that we can take as M the cotangent bundle of a surface, or also more general manifold. And as omega, you take exactly the same formula, dpi wedge dqi, where now the qi are simply local coordinates on sigma, and the p's are the associated momenta. Okay, so it's like computation one has to do that. Actually, this omega does not depend on the coordinates and gives you a well-defined symplectic form. And for us, it's important because, as I was mentioning before, we recovered the equation of geodesity. So now if you consider as G some metric on sigma, then we can associate to G two things. One is the duality between tangent and cotangent bundle. And the other thing we can associate is the kinetic energy. Okay, so this is just the 1/2 square of the norm of P, where we take the norm on the dual space. And then this is also a very nice result, is that if you have a flow line for the Hamiltonian vector field of this Hg, this is exactly obtained by taking the velocity vector gamma dot and then bringing it to the cotangent space using the duality, where this gamma is simply a geodesic for the metric. So we start to see that there's this nice connection between these two words. Very good. So now we saw that some dynamical concepts, so ODs, and now we have to make the geometry enter the picture in some way. And this is done by introducing a group of transformations of our space. So this is a bit like in this famous Erlangen's program, where you basically have a space and have a group of symmetry of the space, and then you study geometry by studying basically how this group acts on the space. So for example, classical example, you have like As a space, you have the plane, and then you have the rigid motions, and then this is a group and gives you some kind of geometry. But then you can take another group. For example, you can take affine transformations, so you get like another type of geometry. And we want to explore something similar here. So for us, the group we are looking at is the group that preserves the symplectic form. So this is this so-called group of symplectomorphisms. And then there is this this fact that basically also maybe you also encounter this group maybe in when you study classical mechanics, because these are exactly the maps that preserves Hamilton equation. No? And the reason is clear, because Hamilton equation basically are given by the symplectic form. And now this symplectic form, you want to understand a bit the geometric meaning. Okay, so this is a two form, so it can be used to kind of integrate and give some measure of two-dimensional objects. But then you can also start taking like wedge products of the omega 0 with itself, so omega 0 squared, and so on. And in this way, you can start measuring also not only two-dimensional objects, also four-dimensional objects, and so on, until you arrive at the top dimension, where at the top dimension, basically you are just measuring the volume in your space up to some factor, which is here n factorial. So this tells us that our group G is contained in the group of volume-preserving diffeomorphisms. So these are the maps preserving the volume form. And the basic question in symplectic geometry is to understand the difference between these two groups. So when the dimension, when n is bigger than 1, then these two groups are different. And we want to understand how different are they in some sense. And recalling what we were saying before, how we can see this group acting on the space, then you can see the difference by comparing how these groups actually act on simple subset. And here one can start looking at the ball. So we can take the ball B2n of radius 1 and see what's the image of this ball under the under these two groups. So if you consider now the group of volume preserving diffeomorphism, then you have a lot of freedom what this ball can do. So for example, if you consider a cylinder, infinite cylinder of radius r, okay, so it's here orange in the picture on the left. You can always basically find a map sending the ball inside the cylinder, no matter how thin the cylinder is. Okay, so no matter how small this r is, you can always basically squeeze the ball in this in the P1 Q1 direction and expand it in the other direction, so that in a volume preserving fashion you will send the ball inside the cylinder. And now the question is that if you can do the same thing using using symplectomorphism, and this is the answer to this is no, and it's given by this famous Gromov's no-squeezing theorem, which basically in a kind of quantitative way can be reformulated as follows. So if you take any symplectomorphism phi, and then you see what happens to the image under the ball of the symplectomorphism, then the shadow here is given by this P2 that this image will have on the plane Q1, P1 will have always a big area. So you cannot make this area small. It will always be bigger or equal than pi, which is exactly also the area of the two ball. Okay, and then basically if you look a bit at what this means, it means that now you cannot find a map sending the ball inside a cylinder of a smaller radius, because if you can put in a cylinder of smaller radius, then this projection will have area not bigger than pi r squared, and this would be a contradiction when r is less than 1. Okay, so this gives us this striking difference between the two words. And as I was saying before, you can use this omega 0 also to measure volumes, two-dimensional things, but also things like in the middle. And then there was a question that also originated, I think, shortly after this Gromov non-squeezing, if some kind of non-squeezing phenomena exist also in this intermediate dimension. In particular, now, if I consider the projection on the 2K coordinates, Q1, T1, Q2, P2, and so on, is it what can be said about the volume of this shadow? No, this shadow in 2K dimensions. And actually, there is here the first known results are results about squeezing. So actually, you can squeeze in this 2K dimension the ball as much as you like. So this means that for every epsilon bigger than 0, you can always find some map phi epsilon such that the shadow of this, the image of the ball, has always 2K dimensional volume less than epsilon. Okay, so this is in contrast to what we saw in dimension 2. And then one can but look now if what we know about this map phi epsilon. And actually, this map phi epsilon that was constructed by Abbondato and Matveyev, I think using some arguments also by Larry Guth. This was it's a map that folds the ball a lot. No? You can imagine this as like a map which folds the ball in a very wild way. And so there was the suspect that then if you have like some less wild map, then still some no squeezing hold also in the intermediate dimension. And Abbondato and Matveyev, for example, showed that if phi is a symplectomorphism which is linear, then you have no squeezing also in the intermediate dimension. And Abbondato and myself could show now almost 2 years ago that actually you can upgrade this to maps which are close to be linear. So now if you take your favorite linear symplectomorphism, phi 0, then if your phi is close to this phi 0, the volume of the shadow will always be bigger or equal than the volume of the ball of the corresponding dimension. Okay, so this shows there is some kind of no squeezing close to linear maps. And here, as maybe as I was mentioning before, for the case of the systole on S2, one maybe wants to know what is the middle ground. So globally, something does not hold. Locally, it does. Where is the middle ground? And right, this is exactly what I wrote here in this question. And one conjecture is that actually like a big set where the non-squeezing holds in the intermediate dimension is where the image of this ball is actually convex. Also, if you remember, I was telling you that the phi kind of makes a lot of, folds a lot to the ball. Then if you know that the image is convex, then you don't have this folding phenomenon. So you can think a bit about this. So this is the first conjecture of this talk. And then we will see later that there are some other conjectures that will be related to this one. Okay. So this is like a first part. And now I want to go in another direction. So kind of going into quantifying, finding a way of quantifying the Gromov non-squeezing even more. So this is done by now introducing what does it mean to measure something from a symplectic point of view. Also, Gromov non-squeezing theorem is saying to us in certain sense that a ball of radius 1 is not smaller or maybe bigger than an infinite cylinder of radius 1/2, say. And now we want to quantify this notion of big and small in symplectic geometry. And if you do this in a very axiomatic way, then it's you come to the definition of symplectic capacity. So Symplectic capacity should assign a measure to every subset of phase space. And what are the intuitive properties it should have? So if I have a A1 in A2, then the capacity of A1 should be smaller than the capacity of A2. It should be something which is symplectic, invariant by symplectomorphism. So if I take A and the symplectic image, then the capacity should not change. The third property is that in some sense it should rescale as the symplectic form. So if I rescale a set by R, then the capacity should also rescale by R squared, like the symplectic form would do. And the fourth property is that in some sense this should measurement should encode the Gromov-no-squeezing theorem, meaning that the ball and the cylinder of the same radius should have the same size. So in this case, normalized to be pi. And then it's nice to observe that the existence of the capacity is actually basically equivalent to the no-squeezing theorem. And moreover, given the no-squeezing theorem, you can cook up very explicitly two capacities, CB and CZ, which are called the ball and the cylinder capacity. And actually, from the definition of capacity, it follows that all other capacities will lie in between CB and CZ. Okay, because I didn't mention it explicitly, but so we are not saying here there is a unique capacity, so we are just giving some definition. And then there might be like more than one capacity. Okay, and the definition of CB and CZ are kind of basically done using the Gromov-no-squeezing. So CB is just basically you look at the biggest ball you can fit symplectic into your set. And CZ, you basically look at the smallest cylinder that you can embed your set into in a symplectic way. Okay, and already this axiomatic definition basically sometimes forces you the value of the capacities on some sets. No? Here I gave the example of the ellipsoid. No? So if I have an ellipsoid, so this is something that from a geometrical point of view is clear what it is. So you just take a positive quadratic form, you take less or equal than 1, let's say. And for example, you have one quadratic form we saw above. Yeah.
Sorry, I'm just interrupting. There's a question in the chat from Buster Porter. If any set is designed to number, or do you need some kind of measurable sets for the capacity? Like you write it as every set has a symplectic capacity.
Yes, so I wrote as every set because then you can, in some sense, once you have a capacity, you can like kind of extend it to every set in some kind of continuity way. But actually, it would be, we will see that in a very realistic way, we can compute this capacity or estimate it only in a very small class of sets, which, for example, is inside measurable sets. So I didn't want to say explicitly the class of set I'm considering it, but we will see that we will look at this in very special sets.
Great, thank you.
Yeah, thanks for the question. And right, so as I was saying, for the case of ellipsoid, then you already basically know the capacity, because if you have an ellipsoid, this was this HA less or equal than 1/2. Let's go back to the definition here. No, so this was the definition. Then basically, if you order the A's starting from the smallest to the biggest, then you see that setting HA less or equal than 1/2, you will contain the ball of radius square root of A1 and be contained in the cylinder of radius A1. And then, but you know, by the definition of capacity, these two sets have the same capacity. And so you are sandwiched between these two sets. Also, the capacity of the ellipsoid is the same. It's pi A1. So it does not depend on which capacity I choose. In particular, this already gives you some motivation for this second conjecture, that all capacity coincide on convex bodies, whereby convex body, I mean like convex set with which is compact and with non-empty interior. So these are kind of the sets that we will see today appear a lot in the discussion. Right, so this gives already a hint that why people started thinking about this conjecture. There is also another hint is this nice observation by Ostrover, which I took from a paper by Hutchins, Guth, and Ramos. Is saying that also if you assume that your set convex body has some symmetry by rotation, and here by rotation I mean just take your R to N, sorry, just take R to N and think R to N as the complex space Cn, and then you have the multiplication by complex numbers, and then you can just consider multiplication by complex numbers of modulus 1. So this gives you some transformation of the space, some kind of symmetry. And actually the conjecture here is true if your convex body has this particular symmetry. Okay, so this is another motivation. But in general, kind of computing capacities is like kind of hard task. So if you have some symmetry, for example, in this case, you can do, and also in this paper I was mentioning by Hutchins, Guth, and Ramos, they also exploit symmetries to find capacities in some cases. But in general, it's kind of a bit of a hopeless task. So the best thing you can do is try to estimate this capacity. And one way to estimate this is by comparing it with another type of measurement that you have at your disposal. In this case, is the volume. So we saw that volume also is a symplectic, has a symplectic meaning. So a way is to compare these two things. So, for example, you can see what happens for ellipsoids. The capacity of an ellipsoid we saw is pi A1. And then you kind of raise to the n power to make it homogeneous with the volume. And now the volume of ellipsoid by using standard mathematics is just the volume of the ball times this A1 times AN. And so in the end, you see that this is less or equal than 1 and is equal to 1 exactly when all the A1, AN are the same, meaning that you're looking now at the ball, a very special ellipsoid. And so this brings us to this third conjecture, which was formulated by Viterbo in the year 2000, saying that if you have any capacity C, then for all convex bodies, this ratio C, the capacity to the n divided by the volume, by normalized with this constant n factorial, should be always less or equal than 1. And here is a typo. And it should be equal to 1 exactly when A is symplectomorphic to a ball. Okay, so this, you can think about this as being motivated by the example above. Still, here you see now some kind of similarity with the case of systolic inequality in Riemannian geometry. So we also here we're considering this ratio between some measurements. So before was the systole, now it's the capacity divided by the volume. And actually, almost by definition, this conjecture holds with the ball capacity. Now, because basically the ball capacity is saying it's giving you the biggest ball you can fit inside. And then once you have a ball of a certain radius, then you can also estimate the volume from below. And then you have equality exactly when this ball basically fills the whole thing, which means that you are actually symplectomorphic to a ball. And also you see now a nice interaction between this conjecture and the conjecture about the fact that all capacity should be equal on convex bodies, because now you know conjecture 3 for the ball capacity. If all capacities coincide, then you know conjecture 3 for all capacities. So then you see that conjecture 2 is stronger than this conjecture 3. Okay, so now again about motivation about this conjecture 3. The one we saw in the example. Another thing is that basically, if you have a convex body, you can always approximate the convex body with ellipsoid. This is like a procedure called approximation by John Loebner ellipsoids. And also here it's nice that Loebner also pops up in this other context as in the previous talk. And basically, we know that the convex body can be very good approximated up to some error by ellipsoids. And so one expects that this conjecture 3 holds up to some error. And this is actually what Arnstein, Avidan, Ostrover, and Millman prove. And basically show the inequality with some constant, which does not depend on the capacity or on the dimension, but still what remains open to prove that this constant here can be taken to be equal to 1. Okay, so very good. So as I said before, capacities are interesting but difficult to compute. And now we see that we can use periodic orbits to build capacities. Okay, so this will give like a way to use Hamiltonian dynamics, Hamiltonian systems, which we introduced right at the beginning of our talk, to define capacity, so a way to measure things in symplectic world. And how does this goes? So first of all, let's recall the conservation of energy that we observed at the beginning. So the Hamiltonian is an integral of motion. This means that if I take now an energy level, so all points with energy equal to small h, then this is invariant by the flow. So this means that I can now look for periodic orbits, for example, in this specific energy level, which in the following I will take to be like smooth submanifold and compact. Now, otherwise you find, if you remove compactness, you find easily counterexamples, and also regularity is something nice because we want to use some differential geometry. So we want this to be regular. And then one of the foundational results is that actually, if you look now at orbits on this particular energy surface, then up to time reparametrization, then they are determined only by the surface, not by the Hamiltonian. So if I take now another Hamiltonian, having S as energy surface, then the two flows, phi h and phi h prime, let's say the other Hamiltonian is called h prime, are the same up to time reparametrization. Okay, so this means that, for example, the orbits traced on the hypersurface are the same geometrically, and if one is periodic, then the other one is also periodic. So this problem of looking for periodic orbits depends only on the surface. And actually, this is confirmed also by the so-called Maupertuis principle, because a very powerful tool in Hamiltonian dynamics is to use variational principles. So this is so-called least action, which basically says that motions with certain boundary conditions are can be described as critical points of some action function. And here is one can find a version that fits very well with this with our discussion. And it needs additionally a one form lambda, which is a primitive of omega 0. So if I now take a one form with this property, then one sees that you have a periodic orbit on the hypersurface if and only if Z is a critical point of the action, which is just obtained by integrating lambda along a loop on the surface, which is immersed. Okay, so if you look inside this class of loops, so loops in the surface which are immersed, and you look for critical points, then you find exactly the periodic orbits for your Hamiltonian flow on the hypersurface. Now, the problem, so this is very nice geometrically, but actually in practice it's difficult to apply this principle as it's stated, because one problem is that you don't know which period you expect from your periodic orbits. Also, and when you do calculus of variation, then most of the times you work with an infinite dimensional space. So you need some compactness properties. And then if you cannot give a bound on the period, then you run into problems by having cases where you don't have periodic orbits. And this actually can happen. So there are actually examples where there is hypersurface with no periodic orbits. So you need to impose some conditions on the hypersurface. And one such condition was kind of highlighted at the end of the 70s by Einstein, is the so-called contact condition. So you require that lambda, the one form, is positive in the direction of the Hamiltonian vector field. And why this is helpful? It's a bit now intuitive, because now it means that you can control the period by the action of the orbit. No? So if you know something about the action, you know something also about the period, because lambda is positive in the direction of xh. Okay, and what it tells me now is also that I can consider the minimal action of periodic orbits, because now this is a positive quantity, because you're integrating a positive function. You can look now at this systole of S as the minimal action of periodic orbits. And this is a positive number, which could be plus infinity in the case we don't have periodic orbits. But actually, we introduce this contact hypersurface because then for this we have better results. And the kind of the very good result that we have is the theorem of Viterbo from 87, saying that if you have a hypersurface in R2n, which is of contact type, then you will find a periodic orbit on S. So this statement, so being of contact type is something which makes sense on arbitrary symplectic manifolds. So one could wonder if similar statement also on arbitrary symplectic manifolds, but this is still an open question called the Weinstein conjecture, which is known in many cases, but still open. Okay, very good. So now what are now examples of contact hypersurfaces? So now we come back to the setting we are interested in. So we will look at examples in R2n and in cotangent bundles. So in R2n, you have to decide which lambda you take. No, there are several choices you can make. If you take this choice here, so lambda is 1/2 pi dqi minus qi dpi, which in some sense is, you can think of this as a kind of radially symmetric one form, being which is a primitive of your omega 0. Then if your hypersurface bounds star-shaped domain about the origin, then you will be compact. Okay, so, and then here, what is a star-shaped domain? I drew it here in this picture on the right. Means that if you take now every ray from the origin, you will always hit transversally the boundary of your surface S. Okay, and then here as a nice example, you have the case of convex bodies. Okay, so if you have a convex body with 0 in the interior, then you are certainly star-shaped. Then the other setting is the setting of cotangent bundles. So in this case, you cannot take pi dqi minus qi dpi because qi are not globally defined as coordinates. But still, you can take now pi dqi as a primitive. So now what you consider are just things which are Faber-Wise star-shaped. So if A is Faber-Wise star-shaped and contains a 0 section in the interior, then the boundary is of contact type. And actually, so I said before that the Weinstein conjecture is still open, but for this type of manifolds, actually is known. So if you have something like this, then it is known that you have a periodic orbit. Okay, and what are the examples? In this setting, these comes from Riemannian metrics, because now I can take as a domain A just, let's say, all the vectors with norm less or equal than 1, or in this notation, vector with kinetic energy less or equal than 1/2. This is certainly Favre-Weyl star-shaped. And what is more, now if you compute the action, this gives you back the length of the curve gamma. Okay, so if you have here gamma is geodesic. So this tells us that it's this weak systolic ratio, sorry, not the weak systole for G, you can read it now using this notion of systole for the hypersurface Hg equal to 1/2. No? So we built now this bridge between the two worlds. Okay. Right, so now we discussed the examples. Now, I promise that you can define capacities using periodic orbits, and this is exactly what the Hoffer-Zehnder theorem does. So it says that there exists a capacity C tilde with the property that C tilde of A is equal to the systolic systolic length of the boundary of A if A is a convex body. Okay, and here we should also add this C tilde is called the Ekeland-Hoffer-Zehnder capacity, so it should also add Ekeland. This C tilde is called the Ekeland-Hoffer-Zehnder capacity, and so it's built now, you see, using periodic orbits on the boundary of your convex body. And now this is a special capacity, and you can, for example, ask this conjecture 3, which was this inequality above, for the capacity C tilde. No? So the conjecture 3 was it here? No? So this was the conjecture 3. So what you can say about this ratio for the capacity C tilde. And if you can establish this conjecture 3 for the capacity C tilde, then you're already a happy person, because this implies, first of all, the conjecture 1 about the systolic, about the no squeezing in intermediate dimension. Okay, so I will also go back to conjecture 1 above. Yeah, so here's conjecture 1. No? So, which is saying that you have this middle dimension no squeezing if the image is convex. And also this has a relation, this conjecture 3 for C tilde, also to another important conjecture in convex geometry called the Mahler conjecture. And basically this gives us a bound on the volume of convex, on the volume of unit ball for norms. So if you have a norm in Rn, you can consider the unit ball of this norm, let's call it K. But then you also have the dual norm, and then you have a corresponding ball K0, no? K polar is called. And then a bit, the idea is that if you now take a smaller norm, then the bigger norm K, the dual norm will be bigger. So there is some kind of, these two things like play against each other. So if you now take the product of the volumes of the two balls, then you get some quantity that you might expect to be interesting. And actually this is a quantity called the Mahler volume. And the Mahler conjecture says that this volume is always bigger or equal than 4 to the n divided by n factorial. And so here, for example, in this short survey, I explained something more about this Mahler conjecture. So here, maybe I don't have much time to go into the motivation of why this is nice. There's also a very nice blog post by Terry Tao explaining why this Mahler conjecture is cool. But what I want to do now is observe that even though this conjecture 3 for C tilde is still open, we at least know it in a local version. So what we know is namely that if you have now a convex body, which is C3 close to the ball, then you can consider this ratio rho C tilde of A, which you can also call sigma tilde of A in analogy with what we saw in the Riemannian case. And then actually this will be less or equal than 1 with equality exactly when you are symplectomorphic to a ball. Now, this is exactly the local version of conjecture 3 for C tilde. Okay, and in particular, also this implies the local version of the non-squeezing in intermediate dimension that we saw also above. Now, this is what here called theorem 3. Now, so if you recall, this was this non-squeezing in the intermediate dimension for maps which are close to linear. Okay, so this we see now here how they are all connected, the several things. Okay, so this is this result for C tilde. And now I would like to explain a bit how that this result actually comes from a more general picture, which brings us back to the Riemannian case. But before, I don't know if there is any question, maybe before we do this last 10 minutes. If not, yeah, I can.
And continue, and then maybe
yeah, sure.
We'll save the questions for later.
Okay, very good. Okay, so this more general result I was alluding to is systolic inequality for contact hypersurfaces, and also here kind of is motivated by the fact that in this conjecture by Viterbo, the ball plays a special role. No? So the ball should be the maximizer for this systolic ratio. What is so special about the ball? We remarked at the very beginning that the ball has this property of describing the dynamics of n harmonic oscillators with equal frequencies. So all orbits are periodic. And so this is a kind of a Hamiltonian version of being a Zoll metric. You know? So we call then Zoll hypersurface something which has exactly this property. So all orbits are periodic and have also the same action. So this is like really parallel to what we saw in the last talk. And as I was saying before, so the prime example is the boundary of the ball, but also now, thanks to this vocabulary between Riemannian and Hamiltonian, we also know that having a Zoll metric is the same thing as having a Zoll hypersurface in T star C. And then before we can state this more general result, we need still one information, something we didn't still defined, because to have a systolic inequality, we also need a notion of volume for contact manifolds. So we saw the notion of volume for its symplectic world, but also for contact manifolds, actually, you can define this using this one form lambda. And this is given by this formula here, which might look a bit mysterious. And then using this volume, you can also define the systolic ratio by dividing the n power of the systole by this volume. And here you see that really we are doing things in parallel as before. And now, why this a bit funny definition of the volume? Because if now your S is the boundary of a domain in R2n, this volume, by Stokes' theorem, recovers the standard volume of the interior of the domain. Also, if your surface was this surface in T star sigma of vectors of length 1, then the volume of S recovers up to this constant AN, which is a universal constant, the volume of the manifolds downstairs, according to the metric G. Okay, so in this case, you see now that the systolic ratio of S is up to some universal constant, the systolic ratio of G. So now if you discover something about the systolic ratio of S, you discover also something about the systolic ratio of G. And then this local systolic inequality is telling us that ZOL hypersurface are local maximizer for this systolic ratio. So it's really analogous to what we saw in the Riemannian case. Okay, so if I have a ZOL hypersurface, if I perturb it a bit with a contact hypersurface, then the systolic ratio will not be larger than that of the ZOL hypersurface, and equality holds exactly when S is a rated ZOL. And so we see that this theorem 8 gives us the theorem 7. So this was this local Viterbo conjecture here above, but also gives us this theorem 11 from last talk. So this was this local systolic inequality for ZOL metrics, around ZOL metrics on S2. Okay, and actually we did everything in the case of surfaces, but now this is a kind of result which works also in higher dimensions. So you can think also of applying this on more general manifolds having ZOL metrics, higher dimensional spheres, higher dimensional projective spaces, and so on. Okay, so this is, I think, the end result. And in the last maybe 5 minutes, I can give a bit a sketch of the proof. And here will turns out that we have some very striking similarities to the proof of the systolic inequality for the torus by Löfner that we saw in the first talk. So remember, we saw sketch of proof in the first talk about the Löfner systolic inequality on the two torus. And now you can see here also a similarity. So I will just sketch it very briefly, so it's not kind of does not compromise what we say before. This kind of addendum, since we have still 5 minutes. So what is a bit the idea of the proof around theorem 8? So we have here several steps. So the first step is that once you have a contact hypersurface, then you have this one form lambda. And now it's more convenient to restrict lambda to the hypersurface, so consider it as something which really lives in the hypersurface and forget about the symplectic manifold outside. So this is what is done in this step 1. So we consider this alpha. And this alpha gives us a nice way to reparameterize the Hamiltonian flow just by dividing by alpha xh. Now we know that alpha xh is positive because it's contact. So this is something you can do. We get this vector field, which is called the Reb vector field. And then this Reb vector field has these two important properties. So I think this was not important here. So the first property is that in the direction of R alpha, alpha is equal to 1 by this definition here, basically. And the second thing is that R alpha annihilates D alpha. Okay, and this is also not difficult to see, but it has to do with the fact that that lambda is a primitive of omega. Okay, now what happens if your contact hypersurface was ZOL? So now you can call the corresponding form alpha 0. And if you have a ZOL surface, then you have some additional geometric structure. So all orbits are periodic and with the same action. This means that if I quotient by the action of by the flow of the Hamiltonian, I get something which is a smooth manifold. Because imagine that you have maybe this is here sigma, S0. And then all orbits are periodic. So then you can just quotient them, and and get for each of these orbits, you just get a point. So you get this quotient map. This is an S1 bundle because above every point you have the whole orbit. And then actually this alpha 0, one form, is a connection form for this S1 bundle. If you know something about the theory of connection on principal bundles. And when you have a connection, you also have a notion of curvature, which in this case is defined by exactly this equation. So there exists some two form on the base, kappa, such that the pullback upstairs is exactly from the alpha. And then the fact that S0 is contact means that K is a symplectic form on this base manifold N. Also, to have a bit maybe an example in mind, if you had as S0 the boundary of the ball, then when you quotient, then you get as N, you get CP N. Okay, so this is the map. This is a code of vibration. Maybe you know from
-1, maybe. No?
-1. Yeah.
At minus.
Yeah. Right. Thanks. Right. So this is then what we know when the S0 is Zoll. And now let's consider the case we are interested in. So you have Zoll hypersurface and you have a perturbation of it. And then since the two things are close to each other, you can think that they are basically diffeomorphic by some kind of very, I don't know, maybe some graph diffeo between the two. So what you can do now is to fix hypersurface S0 and consider this hypersurface then two different forms, alpha and alpha 0. No? So now your space is fixed and your forms now changes. No? Alpha will be the one coming from S and alpha 0 the one from S0. And now here the crucial thing is that you want to find a normal form for this alpha. No? This brings us back to this things we saw for the Loeffner in the Loeffner's proof. So we want a normal form for alpha. And here the normal form that works for us is to write alpha as some function on the base times alpha 0 plus some kind of reminder. No? So now f is a function lives on the base manifold. And actually for the simplicity for what comes next, we will assume just this reminder to be 0. In the actual proof, it's a bit more involved and complicated. So now the fundamental question is, which are the fibers of this map pi, which are orbits for the red flow of alpha. So we know that all these fibers are orbits for the red flow of alpha 0, but maybe some of these are orbits also for R alpha. So what you need to check here, if you remember the definition of R alpha, is that R alpha and R alpha 0 are parallel to each other. So this amounts in checking basically this condition here. And now, since your alpha was f times alpha 0, you can write down what is the alpha. Now, these are the alphas given by these two pieces. And now, since R alpha 0 is vertical, goes in the direction of the fibers, you see that this second bit gets goes away. And in the first bit, basically, it remains only the first part, P star df. So we're asking when this is 0. So this is 0 exactly when x is a critical point for f. Now in this case, then this orbit, this fiber above x will be a periodic orbit for R alpha. And what is the action in this case? If you look, you have to integrate alpha along the orbit, but alpha is f times alpha 0. So the action is basically f at the point x times the action for the orbits of alpha 0, but all the orbits of alpha 0 have the same action, so this is already the system. This means now that if you take x as the minimum of f, then you have this inequality between the systole for alpha and the systole of alpha 0. So now you see that f tells you something about the systole of alpha, but actually f tells you something also about the volume of alpha. Now, because remember the definition of the volume was lambda wedge d lambda to the n minus 1. Plugging what is lambda, it is f times alpha 0. Then you see that basically you're integrating f to the n times this form k. And now you can use this formula to get the inequality you want, just in the Loeffner case. No? Because now instead of this arithmetic quadratic mean, you use the inequality between minimum and arithmetic mean. So your volume is given here by this integral of f to the n, and now you just say that this is bigger or equal than the minimum of f to the n power. And then it's just, once you have this, it's now just, you use just this inequality here, relating the minimum of f with the systole, and then you are basically done. So this is the idea, and here you see really this parallelism within this case and the case for the torus. Okay, thank you very much for the attention.
Thank you, Gabriele, for the. So thank you very much for the nice talk. Are there questions?
You scroll up one more little bit till the theorem, actually, the statement of the theorem.
And maybe, I don't know, Thomas, do you want to record the questions or maybe stop the recording so everyone feels a bit more at ease?